introduction. Yeah, again, my name is Tianhao Wang. So I got my PhD 1 year ago from Purdue University. So unfortunately, all of my ongoing projects are published when around the time I graduate. So, and my new students just arrived last month, so I don't have newer results to show today. So this is a paper we published 1 year old, 1 year ago. 1 year ago, so it's a 1 year old paper. But luckily, I work in an area that's not very crowded, so it's fine. Being 1 year old, it's still the state of the art. And by the way, if you have questions, feel free to speak up. I love interactions. If you can just speak up, so I can hear. If you just type, maybe Yang can remind me of the question. So so the topic is about data streams and differential privacy. As we know, streaming data is quite useful. Actually, from last month, there is a challenge, a big challenge, like a $1 million prize challenge, hosted by both the US and the UK government. There are two challenges. Both of them are streaming data, actually. So so it's a kind of we want to work on those like a bank data or COVID data, but the data is generated every day, and we want to provide the privacy and at the same time generate some utility. So as we can see, there are many real world applications of those streaming data, and we want to provide privacy of that. A natural way of protecting privacy is to use differential privacy. I guess you all know the background of it. So in 2006, we have a centralized differential privacy. Then we have local setting. My PhD thesis is about local differential privacy, and later we also have a shuffle differential or shuffler differential privacy. So in this talk, I will focus on centralized differential privacy, but I think so in the paper we also talk about the local differential privacy, and although we didn't extend to shuffle differential privacy, I think our technique can also be extended. So it will be an interesting question to extend to shuffle differential privacy. So let's establish some terms. We have in differential privacy, we have two databases. Here we model them as two streams, V and V prime, and they differ in any in one location, and it can be changing from any value to any other value. And here we have this normal differential privacy guarantee, where here the epsilon is what we call the privacy budget or privacy loss. And I typically interpret this delta value as a failure probability. Like, for example, if you are constructing an airplane, you cannot guarantee it's perfect. So you have to tolerate some probability of a failure, like every 10 to the power of 9 hours, there's a failure or something. So here we also have some failure probability. Although it's not very precise to call it a failure probability, but it's okay to just from intuition to understand it as a failure probability. So there's a very small difference. So in the data stream, we have like a stream of different. For example, this is the amount of supermarket purchases, right? So every time slot, or you can think of it as every time slot, right? So 9 a.m., 10 a.m., 11 a.m., and so on and so forth. Or you can think of them as each receipt, right? So the first receipt, second receipt, although the exact timestamp might be different, right? But we don't care about the exact information about the time. We only care about just the amount of just one value. Okay, so it sounds like a not a very strong privacy guarantee, but it has been investigated like more than 10 years ago, and um, and the technique itself can also be applied to other settings. For example, the technique of the existing papers can be applied to, for example, database values, where we want to protect one record. So the technique is very general. If you just apply it to data stream, it may sound pretty weak. That's a limitation I have to admit. So more intuitive understanding of this is I can tolerate the release of the general pattern of the purchases, but I want to protect any normally abnormal purchase. Okay. Yeah, that's the intuition of this privacy guarantee. So the problem definition is to publish data streams as accurately as possible with the differentially private privacy budget epsilon. So it's kind of related to the problem of answering range queries, where we retrieve information where some value is in a specific range. For example, if you take this stream and you want to understand how much money the supermarket make in some specific time, right? So the first solution to this is adding Laplacian noise to each observation, to each value. So we add the Laplacian noise to each of the value, and then every value is perturbed, and then we add them up. So here, this solution, the error is b times n, where b is the maximum possible value among all the values, and n is the size of the range query. So in the worst case, if we want to answer range query in a very long range, then the error could be very bad. So yeah, so both b and n are the shortcoming of this baseline method. So we'll see how we can improve it. The second solution is it was published in NDSS 19. We call it a PAK by the first letter of the last name of the three authors. So it builds a binary interval tree to store the truncated values. So how it does more specifically, it first estimates a threshold theta using the percentile. So we'll show it in more detail later. And the second step is after that is observed, we add the Laplace noise proportional to theta in the binary tree. So let's see how it works. So the idea of using the threshold is that in practice, most of the values actually is seen so this phenomenon is observed in almost all the data sets we examine, we evaluated. So most of the values are concentrated below a threshold of theta, which is much smaller than the maximum possible value b. So for example, this is the in their original NDSS 19 paper, they show this figure where the x-axis is the amount, okay, and the y-axis is the probability. It's a CDF of the amount. So as we can see, like for example, if we take the 90th percentile, we only have like below 200. And if we want to accommodate all the possibilities, we need to have a much larger, a value much larger than 400 actually. So the figure only shows up to 400, 500, but we don't know, right? So maybe some millionaire, billionaire spend a lot of money in one purchase. So we don't know. So the idea is we use a threshold theta smaller, much smaller than b, to reduce the sensitivity, or equivalently, we are reducing the noise of Laplacian noise in differential privacy. And this is a very common practice in differential privacy. I've seen it many times. I've been using it for a long time. And this is a very good strategy in many empirical cases. Okay, and the idea is that it is a trade-off between variance or noise and bias. I will show it in more detail later. So here, the idea is that squared error equals, so theoretically squared error equals variance plus bias square. So if we choose a theta that can give us theoretically the best square error, then empirically it will be the best theta we want to use. So how to find the theta, right? So we in the PAK solution, we first reserve the first n values for finding theta. And then we find the theta that equals to the value corresponding to the 99.5 percentile. So more specifically, we just have a so for example, those are the first m values, and we want to find this value which is corresponding to the 99.5 percentile. Okay. So we cannot just use this value to satisfy differential privacy. We need to add some perturbation. So the users in this paper use the technique called smooth sensitivity SS. So instead of adding Laplacian noise with proportional to a very large amount, we can add a smaller sensitivity. We can use a smaller sensitivity here. So yeah, so this is how we can obtain data. Advantage is that by this way we can avoid the high sensitivity, but due to the use of smooth sensitivity, we need to introduce delta to differential privacy. So it's no longer perfect. And then the second step is to use the binary interval tree.
Hello,
so it's kind of interesting. Yeah.
Hello, can you hear me?
Yeah.
So in the last page, how does the sensitivity defined? So is it defined to which quantity?
Yeah. So
is
I
it with respect to the threshold?
Yes. Yeah, I didn't go into details about this SS.
So actually, so when we use small sensitivity, so typically small sensitivity is, so when we use small sensitivity, we use Corsi distribution for noise. So why here you use the plus noise?
Let's see. Yes, I think we are using Cozy, or I don't know. Yeah, actually I forgot in my implementation. So it's a kind of a rough idea. So yeah. it can be Cauchy instead of Laplace here. So I didn't go into detail in smooth sensitivity. Actually, it's already performing pretty poorly from my observation. Yeah, so I'll talk about how to focus on how to improve it later.
Okay.
Yeah. So once we get theta, the next step is to use this binary interval tree. Yeah, so it's also kind of interesting that I think this is a pretty natural idea, but it was only formally published after 5 years after differential privacy was formally published. So yeah, that's kind of interesting. But the idea is very natural, right? So we want to we have eight 8 values, and we want to answer range queries. So the idea is to build up a hierarchy, so that, for example, in here, to compute the sum of the first 7, previously we need to add up 7 nodes. Now we only need to add up 3. But by doing this, we need to split privacy budget to each of the level, right? So this is also a trade-off between the noise in each node and how many node you need to add to answer one range query. And in theory, it shows, I think I forgot, but roughly it reduces the dependency of n, right? The range of the range query from I think 2 to the power of 2 to power of 1.5. So it is improving the theoretical bound. Yeah, so this solution has 2 steps, and unfortunately it is not perfect. It has the delta value here. To improve it, we propose our solution called TOPS. So T stands for this threshold and optimizer, and P is for perturber, and it's a smoother. So it's not a whole, it's very new framework, but it's a sort of general abstracted from existing work. So what we do is we change the 99.5 quantile to customize the solution using report noisy max or noisy max, and we also have a customized quality function. And in the perturber step, we change from the binary tree to a different tree, but the idea is the same, but we just add several improvements to the hierarchy. And the third step is just a post-processing step, which helps a bit to the to the final performance. Yeah, so let's examine. Let's first see without adding any noise, which percentile works the best. So this is one data set called the DNS in our paper. So the y-axis is accuracy, mean squared error. We'll keep using this throughout the talk, and the smaller the better. And the x-axis is the epsilon. As you can see, epsilon is very, very small. That's because the data sets we use are typically pretty large, and the problem itself is it's kind of easier, so we can use very, very small epsilon, and the smaller epsilon the better for privacy. So here is the 99.5 percentile in that paper. As we can see, it's not the best, right? Especially when epsilon is small. When epsilon is larger, it's kind of pretty good. And maybe, for example, the 95 percentile in this case is consistently better. So the idea of our solution is to change from keeping the 99.5 value here to a automatic solution to find the theta. Okay. So the idea is that any solution won't be the optimal for all the data sets and for all the epsilon value. So we want to have an automatic way to find it. So our solution, we use this reporting noise in max mechanism. So if you are familiar with the differential privacy, you can you probably know it's similar to the exponential mechanism, where we define a set of quality functions, and each quality function is parameterized by theta, because each theta will lead to a expected error. And here, yeah, so this is the expected error we use. Each theta will lead to a different theoretical error here. And here, finding the optimal theta with differential privacy is our target, right? So to satisfy DP, we need to add some noise to each result, each expected error, and we can pick the best theta. So here, the sensitivity is the max of any expected error instead of the sum of any error in the original Laplacian mechanism. So here, the sensitivity is the max of all, because we only pick up the best one. We only output the best one instead of output all the values. So yeah, so the intuition of quantifying the expected square error is theoretically we can write it as the sum of variance from Laplacian distribution and bias from theta. So because we need to truncate, right? So each value is truncated to theta. This leads to bias. So we want to achieve we want to find a theta that achieves the best balance between the two. So the first approximation we want to use is we take the root of both terms. So this is because if we just take the original value, the sensitivity, even though it's a max of any error, it still can be pretty large, even unbounded, because this bias actually determines the sensitivity, and the bias square is very large. So we want to have a good approximation that takes the root of both terms. So hopefully, the optimal theta in this equation is very close to the original optimal theta. So we can take some approximation here. And then we need to still work on reducing the sensitivity, because this is still pretty large. So we want to ideally change the sensitivity to be 1. So this is pretty much our final quality function. So this term is the square root of variance. So let me. So this term is Laplace, the error from Laplacian noise, right? So because we need to split a budget among this many layers, so this is a layer. So we have a range here. We have the branching factor. So you can think you can assume b equals 2 here. So this is the height of the hierarchy, and we need to split epsilon by this quantity, and the error, the variance of Laplacian noise is 2 times sensitivity being theta divided by epsilon being this value and take the square. So this is Laplace. And then this term is the average number of nodes we need to sum in order to answer one range query. So this is average value. So because each node, the Laplacian noise is independent, so we can add them up. And this is the square root of variance. And this term is where we add more approximation to reduce the sensitivity. So bias is originally hard to quantify, right? So because when we truncate, some values will be much larger than theta. So the bias is pretty large, and some value is smaller. So we need to add up all the truncation to precisely quantify the bias. But that is to give us too much sensitivity. So what we do is we change bias to just the number of values greater than theta. So although the value can be much larger than theta, we just we will just use 1. By this way, we can reduce the sensitivity to 1. Okay, but as you can see, this will underestimate the actual bias. So here we use another term, a constant term C here. It's actually fine-tuned on all the data sets, but we have to add this in order to have a good approximation. And we have another terms here. So R divided by 3 is the approximate the average number of nodes, and M is the first M observations. So we first take the first M observations and count how many of them are more than theta, and we divide by M. So this is a ratio, and then we multiply it by R by 3, and this is the expected bias for all the range, and then we have another term here, and we can reorganize this, right? So we can divide by the whole term by to both, and the bias here is just this amount is sensitivity 1, and this we can reorganize to the other side. And I know that here we just take the negative value of both terms because we want to report the noisy max. So if we change to reporting noisy mean, we can just keep it. So the term is doesn't matter much. So to summarize, this is how we apply this report noisy max to select the optimal theta automatically, and this is how we make the approximations. So in reality, we find, or in my research experience, my bias the experience, I find many problems can be solved this way instead of using smooth sensitivity. Okay, it actually gives a much better result, empirical result than smooth sensitivity. Although it doesn't give a good theoretical guarantee, but empirically it's much better. So let's see first whether the approximation makes sense. So the idea is that this green line is the our approximation, and the blue line is the true squared error. So we take some data we can plot this, right? And we can also plot our approximation. So the idea is that if we can observe that the optimal theta in both cases are very close, we are having a great approximation. Yeah, indeed, we observe is pretty close, so that's good. And also, we observe that there is indeed a optimal theta because here it's a noise grows grows with the theta, and the bias decreases with the theta, right? So because bias, the larger the theta, the smaller the truncation you add. Yeah, so the second step we improve over the existing method is we use a better fan out. So originally, this is the original tree, binary tree. And we take the result from this paper, actually my advisor's paper, and we just use a very flattened tree. So it's a fan out of 16. This paper proved this 16 achieves best solution. So this is another place where theoreticians does not care much because asymptotically this is already the best, but practitioners should care because if you instantiate every terms, every constant, then 16 it actually gives the best variance, gives the best result, the squared error. So the next step we take to improve the hierarchy is to enforce consistency. So the idea is that we add an independent Laplacian noise. As you can see in this example, they are not consistent, right? So 6.8 plus 3.2 should be equal to the parent node, but it doesn't. So this paper actually 12 years ago proved that by leveraging the prior knowledge that the tree has to be consistent, we can actually improve the overall empirical result. Okay. Yeah. So if we can make it consistent, we have a better result. And also another benefit of enforcing consistency is now we can just take the layer. We can not just take the leaves, right? Because if we take any internal node, after consistency is the same as the sum of all its dependent all its dependence nodes. So we can just take we can delete all the internal node and just use the final node as our streaming output. So the one disadvantage of this this paper is that it has to be offline, right? So it has to be after we have all the hierarchy available, we can apply some algorithm to make it consistent. But our observation is that we can easily make it online. Okay, so by making it online, the benefit is that we can output the streams in the online setting instead of after waiting all the maybe after waiting for 1 day, 1 month, 1 year before we can have access to the DP data. So by making it online, we can observe every output instant. So that's pretty useful in many cases. So how we do this? So the observation is that every node is consistent of the true value plus the noise. And the true value is naturally consistent. So what we can do is we just make the noise consistent. Okay, and if the noise is consistent, we just add them up back to the true value, and the whole hierarchy is consistent. So what we can do is we generate the noise beforehand, before any even one value arrives. Okay, so we generate all the noise, And in the backend, we make them consistent. And this does not violate the differential privacy because because the result after we add it back to the true value, the result is exactly the same as if we do online consistency because the this can be disentangled into two, and we make it consistent, and the result is exactly the same as we just do it in the offline setting. So if the offline setting is differentially private, the online setting is also differentially private. So we prove is exactly the same as the result in the offline setting, and it's differentially private, and it's online algorithm. Some evaluation we took some evaluation. So I should admit that it's hard to find a good data sets in this problem, and I've been struggling a lot to deal with the data sets. The result is not very stable in a sense that I add some modification to the dataset. For example, I want to support infinite streams, but all of them are not infinite. So what I can do, right? So I have to repeat. I have to duplicate the stream many times in order to support a good, a pretty long coverage. Yeah, so there are many small modifications to the dataset, and but the code is available, so you can have the dataset, and the code will do those small modifications. So here is a result for DNS data. As you can see, this is the true stream. Here, each point corresponds to, I think, 9,000 original points. And our result can pretty accurately recover the original stream. And the previous solution is not as good as ours, obviously. Otherwise, we cannot publish a paper. So let's see exactly which step is the most effective, right? So we have many steps. Actually, not many, like 5 steps of improving the original paper. But which one is the most effective, right? So here we show in the same DNS dataset the original method compared to our new perturbation method, right? So I changed the hierarchy and also add another smoother method, which I didn't discuss today, but it adds a small improvement to that. And this is our threshold optimizer. So we change from smooth sensitivity to a solution based on reporting noisy max and approximation. And this is our final solution. So as we can see, threshold optimizer is a major improvement, and the new hierarchy is also pretty good, but not comparable to the threshold optimizer. Right? So it's already 3 orders of magnitudes better, but threshold optimizer is almost 10 orders of magnitude. So it's a huge improvement. Yeah, so, and finally, this is our final solution. It's a combining of the 2 improvements. It's even bigger improvement. So here I show several intermediate solutions based on the hierarchy. So this is a baseline that always outputs 0, and this helps us like determine if a method is giving a reasonable, meaningful result. Because if we are achieving even worse result than the baseline, it's meaningless, right? And this is the original binary tree. It's good, but our Final 16 is better. Yeah, and our online consistency is improving even more over the best hierarchy. And the perturber, sorry, the smoother, which I didn't talk about, is just adding some post-processing to make it even better. Note that the post-processing is also online, but yeah, so it can make it better, especially when epsilon is small. To conclude, this is the end of my talk. Thanks. We in this paper talk about how to improve methodology for outputting streaming data. It's a kind of a old school problem, but the good news is that although it's less crowded and it can be the state of the art for a long time. So in the paper, we also extended it to the local DP setting. And I think it's also interesting to extend it to shuffler DP setting. And I think there are many different problem definitions in this area. So in this case, we just consider two neighboring streams to be differing in one location, and the difference can be as much as possible. But in some problem definition, they assume the difference is at most 1. So sensitivity is 1. So there's no need to have a better threshold optimizer because sensitivity is already 1. And it's assumed in the definition. So, and also we are also looking into how to use the sliding window based differential privacy, meaning that although we have an infinite stream at any window, and the window is sliding from the beginning to the end, there is one or a fixed amount of change. And there are many different solutions, like much stronger definition called the user level DP, where two streams can be very different. And in this case, it's much different and much difficult. Yeah, so I think this is what I talk is. It's a quite interesting area, and look forward to your questions.